Okay, continuing with our multiple choice practice test. We have a function that's defined as a piecewise function, natural log of x between 0 and 2, and then x squared natural log of 2 between 2 and 4. It says find the limit as x approaches 2. So if we think about finding a limit for a piecewise function, we can treat it like a full limit is going to exist if the one-sided limits on both sides of the graph are approaching the same y value. So we can find the one-sided limit separately, one for each of the functions from the appropriate side. Right? So as we're approaching 2 from the left side of 2, like 1, 1.5, 1.9, that all falls within the range of 0 to 2. So limit as x approaches 2 from the left side of 2 is going to be with natural log of x. And limit as x approaches 2 from the other side of 2, like 3, 2.1, 2.0001, that's going to be within this interval, and that's going to be for x squared natural log of x. So we're going to evaluate the limit, and when we evaluate limits, we don't do anything with the one-side limit algebraically. We just plug the number in and see if we get a real number. So we get natural log of 2. That means from between 0 and 2, this natural log of graph is heading towards natural log of 2. But this graph, which exists from 2 to 4, is moving towards a different y value altogether. So one piecewise function is moving towards y value of natural log of 2. The other is moving towards 4 natural log of 2, and there's a disconnect. And because of the disconnect, the graph doesn't have to exist at that point, but it does have to move towards the same y value. And in this case, these do not agree. So because the one-side limits do not agree, we can say the full limit does not exist. Okay, number 13, we have a graph of the function f shown. There's a vertical tangent at 2. That just means that the slope does not exist at that point. And it says for what values between -2 and 4 is the graph not differentiable. So differentiable means that it's not a smooth curve. So if a function is not continuous, that also falls under not differentiable. So here we see it's a smooth curve all the way through, but there's a break at 0. Smooth curve all the way through, there's a vertical tangent, so that means the slope doesn't exist, so it's not differentiable. So not differentiable at 0 because it's not continuous, not differentiable at 2 because it's not differentiable, meaning that it's vertical tangent, slope doesn't exist. So we have x equals 0 and x equals 2. Those are the places where graph is not differentiable. Particle motion problem. We have a particle moving along the x-axis. Position is given by x of t, t squared minus 6t plus 5. For what value is the velocity of the particle 0? So if I want to find velocity, I'm going to find the derivative to get from position to velocity. So the first derivative, we get 2t minus 6. We're going to set the velocity equal to 0. And we get 2t equals 6, so t is equal to 3, and that's our answer. Okay, number 15, we have f of x defined as the definite integral from 0 to x of square root of t cubed plus 1. We're trying to find f prime of 2. So if I want to find the derivative of an expression that has a definite integral in it, we're going to be applying second fundamental theorem of calculus, which basically says if I want to find the derivative of a definite integral, these two operations cancel each other out. This f of t remain largely unchanged, but the upper bound does get evaluated into the function. So the result is going to be f of p of x multiplied by the upper bound's derivative, so times p prime of x. So back to our function. We want to find the derivative. So to find the derivative, we have to, it's going to essentially take away this integral procedure, integral notation. And we're just going to follow the rule here. So we started off with integral of square root of t cubed plus 1. We want to find the derivative. So the upper bound gets plugged into the function, f of p of x, that becomes x square root of x cubed plus 1, times the upper bound's derivative, so x's derivative becomes 1. So we get square root of x cubed plus 1, that's the derivative. And then one step further, we're trying to find the derivative at 2. So once we have our derivative expression, we can plug 2 in for the x. 2 cubed is 8, 8 plus 1 is 9, square root of 9 is equal to 3. Answer choice D. Okay, number 16. We have f of x equals sine of e to the negative x. So a couple of, it says find f prime. A couple of reminders. The derivative for sine of u is cosine of u times u prime. The derivative for e to the u is e to the u times u prime. So let's go back to, this is a chain rule, outside's derivative times inside's derivative. So outside's derivative is sine u's derivative, which is cosine of u. And then we're ready for the inside's derivative. So e to the u's derivative is e to the u times u prime, so e to the negative x times negative 1. So we have our derivative. We just have to clean this up a little bit here, push the negative and the e to the negative x in the front, and we can make it match answer choice E. All right, for 17, we have a function f of x provided. It's twice differentiable, so smooth curve here. Okay, which of the following is true? And all this is pairing information about the order pair, the slope at that order pair, or the concavity at that order pair. So if we look at f of 1, we see that's clearly just going to be at the x-intercept, so f of 1 equals 0. F prime of 1 is asking, what is the slope of this graph at x equals 1? Now, we may not know the exact slope value, but we know that this is a part of a positive slope. So whatever number this is, it must be a positive slope, positive number. So we know f prime of 1 is going to be a positive number. Now, f double prime of 1 is asking, what is the concavity of the graph at x equals 1? Now, if we take a step back and look at the shape of this graph, the curvature of this graph, this is curving downward, so this is part of a concave down graph. So concave down for second derivative means that it's a negative value, negative second derivative value. So if we compare these values, 0 versus a positive number versus a negative number, then if we want to put it in order, the negative number is going to be the smallest, followed by 0, followed by the positive number. Okay, so number 18, an equation of the tangent line to the graph of x plus cosine of x at 0.01 is, so if we want to find the tangent line equation, we're going to first find the derivative function. And then from the derivative function, we're going to plug 0 in to get our slope. And then from there, we can put into point slope form once we gathered all the information that we need. So to find the derivative, go through power rule, x becomes 1, cosine becomes negative sine of x. Once we have our derivative formula, we can plug 0 in to get our slope. So 0 plugs in for x. Sine of 0 is 0. 1 minus 0 is 1. There's our slope. Order pair is provided for us at 0, 1. So once we have our order pair and we have our slope, point slope form, and then rearrange it, solve for y so that we can easily match our answer choice. Okay, so number 19, f double prime is given to us. Then the graph of f has an inflection when, so let's go through our steps. If we want to find points of inflection, we're going to find f double prime, which is given to us. We're going to set f double prime equal to 0 so that we can find critical points. But let's make sure we don't stop there. Just because we find critical points, that just means that we have a candidate for point of inflection, but not all critical points is guaranteed to be a point of inflection. So we have to make sure we do the additional checks necessary. So we're going to create a f double prime sign line, and then we're going to test intervals in each of the regions. And then point of inflection is going to exist at the critical points if that critical point has a sign change on either side of that x value. So we take our second derivative function, right? We set equal to 0. We find our critical points. The nice thing is that these are all factored forms, so we can set each part equal to 0. We get x equals 0. X plus 1 is, we get x equals negative 1 there, and we get x equals 2 here. Okay? We populate our second derivative sign line, so negative 1, 0, and 2. And now we're going to choose values in each of these regions to plug into the second derivative function. So if I plug -2 in for x, I get negative times positive. The nice thing, this term is always positive, so this is not going to affect, we don't have to test this. This always, parentheses will always be positive. So negative times negative is positive. Okay. Next, we plug in -1/2. So -1/2, that's negative times positive, which is negative, so concave down. Next, point over, interval over, we test 1. So 1 times 1 plus 1, that's positive, positive times positive, which is positive. That's concave up. Okay. We can test 3. Positive, 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 so positive. So concave up, concave down, concave up, concave up. So not all critical points is going to have a change in sign. There's no change in sign at x equals 2, so x equals 2 is not a point of inflection, only at -1 and at 0.